In general, we call noise unwanted sound, and we measure that in by measuring the pressure level that you would hear. In general, we use dBA, which is decibels, and an A-weighted scale, A meaning the pretty much the thresholds of human hearing. Other types of sound pressure, or SPL, measurements exist, bells, I forget the others, but in the text on the tables you usually see dBA, and that's generally measured in an anechoic chamber, and built to an ANSI standard, and which I think, well, I don't know the standard offhand, and then the actual test itself is measured to an ANSI standard. What most manufacturers do is, most noise comes from the exhaust side or from the inlet side, and if you reference from either side, it comes down about 50% or more in general, of course, and that's where you'll see most of the testing done. Most manufacturers test about 1 meter to the side, or 1 meter to the side. What else is there? So that's how it's tested. Noise comes from basically three sources. The first one we're going to talk about is mechanical, then we'll talk about aerodynamic and electrical. So let's talk about mechanical noise for a minute. Mechanical noise, for the most part, comes from, I should say, for low-speed fans, you're going to hear bearing noise, which is either the balls running around the bearing in the bearing as the fan turns, or a rubbing of the shaft on a sleeve bearing. Newer type fluid bearings, very quiet, originally designed for the VHS industry, and fan manufacturers use those. Best life comes from ball bearings. That's about 30% more than a sleeve bearing, and then fluid bearings are somewhere in between those two. The advantage of a ball bearing is that you can mount a fan in any direction. A sleeve bearing you cannot mount like this. Same with a fluid bearing. They're pretty much designed to operate with a shaft in a horizontal position, but I digress. The higher speed fans, and you're seeing the back of my bald head, which I'm very conscientious about. The higher speed fans, you'll get vibration from radial, so that's kind of the out of balance condition, kind of like if you were driving down the road with a bad tire, you'd feel the car shake. Same thing idea here. Manufacturers reduce noise by improving balancing usually in one plane on fans, usually close to the inlet side, and on high-end, say, military aerospace fans, they'll balance it in two positions, and that will reduce that quite a bit. Some of the vibration you may get is a axial vibration running in and out on the axis, which is, in general, has to do with the radial component of vibration. So that's what you get on those. So, yeah, and the most of the noise you'll hear depends on the mass of the unit that you're, the mass of the fan and the mass of whatever you're mounting to. If the mass of whatever you're mounting this fan to is fairly low, you'll get a lot of vibration, or there'll be an attenuation of vibration between the fan and the unit you're mounting it to. And so, as ergo, you see, we're going to talk about the isolation strategies for that. That covers that portion. So let's talk about aerodynamic noise. Aerodynamic noise is very limited things you can do for that. Basically, aerodynamic noise is a whistling of air you get due to pressure differentials between the pressure side of the blade and the suction side of the blade. The pressure side of the blade being the exhaust side of the blade. so that pressure differential plus the material that's used for the blades, sometimes making a more flexible blade reduces noise. Adding glass to the plastic, making it more rigid, will make it ring. But by far the largest component of noise in fans is the aerodynamic portion. So there's two strategies to deal with that, well actually three from our point of view, from the user's point of view. One would be to change the rotational speed up and down. Speed has a lot to do with how much flow and pressure you get. Flow goes up with directly with speed. You increase the speed, you increase the flow 10%, but you increase the pressure 1.2, or well, with the square of that, or 20%. But you also increase the power required to do that by the square of that, or 40%. So you can see how that works in either direction, up or down. So I'd say the major way to do it is to bring the speed up or down as required. You can also change the diameter. Not too many people talk about this, but this is a 39 CFM, 34 CFM 92 millimeter fan. If I want that same flow from the next standard size up, which is a 120 millimeter fan, I can drop the speed with the square of whatever that is. So if this fan is spinning at about 1,000 RPM, I want the same flow from a 120 millimeter fan, I could drop that down to about 800 or 700 CFM, get the same flow and much less noise. General noise is over my head, so I can't give you the scientific reason, just I can tell you from the textbooks what you get. And the other way to handle noise is to orient duct the flow and orient the fan somewhere deeper in the box or someplace else in whatever it is you're trying to cool to reduce the noise. That covers aero for this purpose. Last component, three components: mechanical, aerodynamic, and electrical. Electrical you usually don't hear much. It's for high-speed fans, you'll see it much more in the throttling of the fan using pulse width modulation, or PWM. Fans generally switch at a frequency of about 300 Hertz between the coils of the motor. But to get a speed control, sometimes users will use a pulse width modulation anywhere from 10 to 40 kilohertz, and so you'll hear the coils sing as you go up and down that frequency. So I think I've given you too much information for what you probably need.